Okay, I think it's just a few of us. So shall we just start ramping right into the exercise? I think before we actually go to the details of the numerical solution of this simple numerical solution of the stochastic growth model, I'd just like to reiterate the numerical approach for computing the integral of the expectation. Remember, expectations are integrals, so computing an expectation numerically means just evaluating an integral numerically. And last week I briefly showed how to do that, and this is where I'd like to continue. So what we need when we deal with stochastic dynamic optimization models is to compute the expectation, which is part of the Bellman equation. So remember, the Bellman equation states that you maximize over the control, and what you maximize over is the sum of the instantaneous utility on the one hand side, plus the discounted expected value continuation value. Okay, so we need the expectation here. And since we do not know the exact form of the value function, we have to compute this expectation numerically in general. Sometimes we do know something, then we can use that. But in general, we do not know the form of the value function, and therefore we have to do the integration numerically. And one way, there are many ways, but one way which I think is usually quite convenient and quite accurate and quite fast is the Gauss-Hermite quadrature method, where you assume that you have a variable which is normally distributed. And if it's not normally distributed, this is still often quite a good approximation. So let's assume that X has a normal distribution with some expectation mu and some variance sigma squared. Then we can compute the expected value of any function of X, not any function, but well-behaved functions, the expectation of well-behaved functions of X, which is defined as this integral, by evaluating the function g of X only at a very small number of points. And the points where we evaluate that function are derived from the so-called Hermite polynomials, which are not really interesting for us here, where they do come from, which we can just use. Okay, so this algorithm will provide us with a number of points. We decide how many points, but say 5 or 10 points are usually sufficient. A number of points where we evaluate the function g of X, plus the weights. And then we simply actually evaluate the function at the points. We have to rescale and shift them if it's not a standard normal distribution, but that's easily done. So we evaluate the function at these points and weigh them by the weights, which are also provided by the algorithm that gives us the points. Okay, so let's look at one example. So first of all, this is already implemented in R. If we use the package rmutil, then there's a command which is called Gauss-Hermite, which will return a matrix where we have the points which are used to evaluate the function after rescaling and shifting, and the weights. And here are just 4 points. This is usually probably not enough, but if we increase that to say 6, 8, or 10, or 5, 7, or 9, then it's quite a good approximation. So let's look at one example how to actually use that. And here we assume that the function where we want to evaluate the normal distribution is the sine of x to the -2. And we assume that X has a normal distribution with expectation 0.9 and variance 0.15 to the squared. Okay, and what we want is the expectation of the sine of this normal distribution to the power of -2. Okay, how do we compute that? This is actually part of the tools slide, which are on the Learn web. So how can we do that? Let me just share a different screen. How can I do that? So let's stop sharing here and then start the R screen. Yeah, that's the one. So we need the package. Can you see that?
Yes.
Because the frame is at a different position now, the sharing frame. Anyway, okay, so we need this library, and what we want is a normal distribution. So we just say create this matrix of Gauss-Hermite polynomial points, say 8 of them. Let's have a look at that. So we get the points, that's the first column of this matrix, and we get the corresponding weights, that's the second column. Then we rescale and shift the first column, which are the points. So let's call them the x points. That's the first column multiplied by the standard deviation. And in the exercise, it said that the standard deviation is 0.15 plus the mean. So this is just linear transformation of a normal distribution. So rescaling by the standard deviation and then shifting by the mean. So these are the points then where we want to evaluate the function over which we take the expectation. And we get the corresponding weights. That's very simple. That's only the second column of this matrix. Okay. And now we actually use these points to evaluate the function. And we compute the sign at these points to the power of -2. We multiply that with the weights, and we sum that up. And here we have an approximation of the integral. Okay, so you can see here that this integral is approximately 0.855. And this is very fast because we have to evaluate the function only at 8 points, which is a big advantage compared to other approximation methods. So different approximation method to compute the mean would be a Monte Carlo simulation, where we draw a large number of points from the normal distribution and evaluate the function at these large number of points. So we can do that as a comparison. So let's suppose that we draw, say, 1 million points from a normal distribution with this mean and the standard deviation. Then we can also compute or approximate the expectation by computing the mean of x to the -2. Well, that's a different approach to compute the expectation. The result is almost the same, not surprisingly, or reassuringly, I should say. But here we have to evaluate the function 1 million times. And the result is almost the same. Okay? So it's much more efficient to evaluate the function at a small number of points. And this is even more so if evaluation is relatively costly, which it could be if we have to interpolate the value function. So comparing these two different approaches, I would say that the first one, the Gauss-Hermite approximation, is much better because it's much faster. Okay.
May I ask a silly question, maybe?
Sure.
So the Monte Carlo approach, so where you just calculated the mean, so the mean is basically the average, right, of all the points that you've drawn. Yeah. So you would never consider, like, I mean, you know, simulating the calculating the expected value of this function, like you would do, you know, using pen and paper. So take the points of the density, multiply them by the by some values of the sign, then sum those up. You never would consider that, because this is also an approximation, right?
That's right. Absolutely right. Yes. So let's go back to the other set of slides. So you can also really compute this function here, g of x times the density function of the normal distribution, and just use any kind of numerical integration for this integral here. That would also work.
But this is too complicated or too hassleful, or
too slow.
Okay.
It makes sense to choose the points where you evaluate this function very efficiently. And these Gauss-Hermite polynomials have certain optimality properties. So evaluating the function at those points with these weights is the most efficient way to compute the integral for a given accuracy.
Which is always, I mean, we're talking about that basically year after year, but this always puzzles me that you just need 8 points to say approximate a relatively or a comparably complex object like the integral or the large sum of the function, which is, I mean, I wouldn't say it's a wonder, right? But it's close enough.
I agree, absolutely.
I also have a question. I think a silly one as well, but library R-multil doesn't really work in my R Studio.
Yeah.
There's some trick or something like this when using this library command, or?
You have to install the libraries first.
Ah, okay. So just install library.
Are you using RStudio?
Sorry?
Do you use RStudio?
Yes, yes.
Then in the bottom right pane, there's one menu item which is called packages.
Mm-hmm.
If you click that,
install,
yeah. Exactly, mm-hmm. And then you can type rmutil.
Okay, and then install.
And then it install, yeah.
Mm-hmm. And then I go.
You can also choose that all the dependent packages should also be installed.
Mm-hmm. Okay.
And then it's installed once and for all. You needn't repeat that next time. But what you always have to repeat is the library command. So you have to type, before you use the Gauss-Hermite command, you have to type library rmutil to activate these additional commands.
Okay, now it's working. Perfect.
Good.
Yeah.
Okay.
Thank you.
That's not a silly question.
Okay.
Okay, any other questions? So let's have a look at the exercise again. So just brief summary. Our objective function is the same as before in the deterministic case. We have the instantaneous utility, which is just log of consumption. We have the capital stock, which evolves in this way. So in a way, this is our production function. We have 100% depreciation per period, and we consume part of what we produce, and the rest is the capital stock for the next period. So then we have this part here, which is interpreted as the technology level, which is random. And we assume to start with that the distribution of the log of the technology level is a normal distribution around 0 with some variance. Okay. So the technology level itself has a log normal distribution. Now that's just an assumption, and we assumed at the beginning that the draws are independent from each other. Then we have two state variables, k and theta. We have the control variable. We have the standard Bellman equation. What's new here is that we have two state variables. Up to now, we only considered one state variable, but everything else is just the same as before. And it's also possible to derive the analytical solution, but we don't. We only use that to compare that when we finished the numerical exercise. Then last week, I already said that we have to solve number of problems. How can we represent the value function? How can we compute the expectation for the continuation value? And how can we solve the maximization problem? So these are, looking at the Bellman equation, these are the steps from inside out in a way. So in the innermost part is the representation of the value function, then comes the expectation, and then finally the maximization. So it makes sense to work in this direction from the innermost part to the entire Bellman equation. Okay, we already did that last time, how to represent the value function. There are many different ways. So here it also would make sense to assume that you know the functional family of the value function, but we assume we don't. And if we really don't know anything, then I think the most natural way to represent the value function is by defining a grid, two grids, one over the capital stock, the other one over the technology level, and then for each pair of these grid points to compute the value function at that point, and just use some kind of interpolation scheme in between the grid points, the pairs of grid points. Okay, and a good, relatively fast interpolation command for bilinear interpolation is provided by the R package fields, and it's called interpolation surface. And well, we talked about that last time. So this is, I think, a natural way to represent the value function. Please remember that we are not working on efficient solutions here. So this is more to understand the conceptual idea by really looking at the program and by really implementing it. Then depending on the problem at hand, to make it faster. And here also we will see that the program is, well, relatively slow. So today we won't see the solution, I guess. Okay, right, so this is the interpolation command. Then how can we compute the expectation? Well, for any given state variables and for any choice of the control variable, the consumption, we already know deterministically what the capital stock in the next period will be. Okay, so there's no stochastics in here, and therefore there's no need to compute an expectation in this dimension. The only stochastic element for next period is the new technology level. All right. Okay, and we have already seen that we assume in the exercise that the log of the technology level has a normal distribution. So it makes sense to use this Gauss-Hermite quadrature method. And we've just seen how to do that. All right, and then finally, the maximization problem. Well, what do we need here? We have to evaluate the value function at each pair of the grid points. So if we have 1,000 grid points in the capital stock dimension and 1,000 grid points in the technology level dimension, then in total we have 1 million pairs. And for each pair, we have to solve the maximization problem. Right? So here you can already see that the number of state variables is very important. And if you have more than, say, 3 continuous state variables, it won't work in general, unless you know the functional form of the solution. So this is the reason why we will look at reinforcement learning methods after Christmas. Okay? But here we have to do that for all pairs of capital stock and technology level. Then we have to maximize, and the maximization, I forgot the discount factor here, so there's a beta missing here. The maximization is just over this thing in the square brackets. So inside we have to evaluate the expectation, and we have to interpolate the value function because we do not know next period's technology level. This won't be on a grid point in general, so we have to do interpolation. And depending on the consumption level, we will not have the capital stock in the next period that is exactly on a grid point. So again, we have to do interpolation here. So we have to interpolate the value function. Then we have to use Gaussian, the quadrature method for the integration. This is simple, adding the instantaneous utility, and then finally maximize that over the consumption. Okay, so we do that for all grid points. So then we store the maximal values in a new matrix. Let's call that value, and that means the dimension, the top-down dimension, and that's a new matrix. Okay. So the grid points remain the same for each iteration of the value function iteration, but of course the grid itself, which is on top of the grid points, this will change from iteration to iteration. That's about it. Any questions concerning this? But if you have a question during the when we look at the program, just ask. So I will share the whole screen again. So let's open okay, so let's go through the program step by step. First, we have to activate these packages because we need the numerical integration for the expectation, and we need the fields package for the bilinear interpolation. Okay, so let's activate these two packages. You may have to install this fields package first. Then in the exercise, the parameter values are given. So the normalization constant for the production function is just set to 1. Then we have one of the elasticities, which is 0.7 here. I think it would be better to make it 0.3, but well, this is just a numerical illustration. Then we have the discount factor beta. We have the variance of the technology shock. We have the grid points. So NK should be the number of grid points for the capital stock. So I set that to 150, and for the technology level 100. So in total we have 15,000 pairs for the grid points. Then I define the grid for the capital stock from 0.05 up to 1, and it's equidistant. This could also be a good idea to make it not equidistant, as Andreas has shown last week. Sometimes it's more efficient to have certain areas where the grid is finer than in other areas. This could be the case here, I don't know. So here it's just equidistant, and the same for the technology level, which is defined here for, this should be the log of no, sorry, this is theta grid is e to the, well, the exponential of the log of theta. Yeah, so theta, the log of theta has a normal distribution around 0 with a small variance. So we put that into the exponential function, which means that we are around 1 roughly. So 0.85 is really far away from the 1, and 1.2 is also far away. So we can be sure to that this grid really covers the relevant area for the technology space. Then for value function iteration, we need an initial guess. And normally the initial guess, if we don't know anything, is just 0. Okay, but then it would really take a very long time to get the final solution, and therefore I used an initial guess which is close to the final solution already. But in theory, we could just input here zeros. The object is defined as a list, and this is because the interpolation command, which is the most complex part in this program, requires a list to define what should be interpolated. And this list has three components: the grids in the x dimension, in the y dimension, and a matrix Z, which tells us the height of the interpolation, of the points that should be interpolated. Okay. And remember, this could also be just a matrix of zeros. But here it's just the, well, it's close to the true solution. But this is really just to speed things up a bit. So just ignore line 23. Then starting in line 25, we define what's in the square brackets of the Bellman equation. So what we used to call the maximum on the slides. And the maximum here is, of course, a function first of the control variable, which is consumption. Let's call that double C here. Then it also depends on the current value of the technology level. It also depends on the value function on the right-hand side, the one which is inside the expectation. So this is the value current iteration, which we use to find the value function for the next round. And of course, the parameters, which are the normalizing constant for the production function, the elasticity, the discount factor, and the variance of the technology shock. Okay, so these are the parameters we need to calculate the Bellman equation, to maximize what should be maximized in the Bellman equation. Then we need to build the expectation. And here I used this Gauss-Hermite expression. So with only 6 points. We use these points to, we scale them up by the sigma, so the square root of the variance. That's the standard deviation of the shock. There's no shift variable because the log of theta has an expectation of 0. So we just use the standard normal distribution points and scale them up, but do not shift them. We put this into the exponential function to get rid of the log. And then these points are the points, these are the technology levels in the next periods where we need to evaluate the value function. So this is theta tilde. And the corresponding probabilities or weights are given in the second column of this matrix M. Then in line 29, we have the transition equation for the capital stock. That's nothing random here, nothing difficult here. This is really just computing next period's capital stock, and there's no randomness, nothing. And then I think the most difficult part is really computing the expected value of the continuation value, the expected continuation value. How do we do that? Well, we use this bilinear interpolation command, which has 2 arguments. The first argument is the current value function object. That's the one we defined up here. Is the object that we want to interpolate. And then we need the point where we want to evaluate that. And the point where we want to evaluate that is k tilde theta tilde. Right? This is next period's capital stock. This is next period's technology level. These 2 points are derived from the transition equation. So the capital stock is just the deterministic transition equation for capital. And theta tilde is just drawn randomly. But actually, theta tilde is not just a single point, but these 6 points here, or rather these 6 points here. So this object here tells us where to evaluate the value function. And there are 6 points where we need this linear interpolation, bilinear interpolation. Next period's capital stock is not stochastic. So for each of these 6 points, that's the same. But theta tilde depends on where we evaluate the technology level. If there are any questions, please ask.
Just to make sure, so we are starting out with 15,000 points in general, but in line 30 we just pick basically 6 of them out of this complex 3-dimensional object, and use those 6 to just calculate the expected value basically of the entire 3-dimensional object, right? In general.
Yes.
Which then is a number.
Yeah. Absolutely right. So we have this very complex object of the value function here with 15,000 points. And we only interpolate that, or we evaluate that, if you like, at 6 different points. But of course, we do that for all pairs of capital and technology. So for all 15,000 points. Yeah, so we need to do this maximization exercise for each pair of capital and technology. So there are 15,000 instances where we have to evaluate these 6 points, which are derived from the 15,000 object value function. That's right. Yeah, but this here is only a single value. This is only the expectation of next period's value function if we start off at capital K and technology level theta.
And the value function is such that the one that we assumed in the first place.
Yes. Yeah. You mean the value function of the current iteration?
Yeah.
Mm-hmm. Right, then we get this single number here, the expected value of the continuation value, and what we return, what the maximum returns, that's the function that computes what's inside the square brackets, is the current utility, which is easy, just the log of consumption, plus the discounted expected continuation value. And the really difficult thing is normally to compute the expected value for the next period. Okay, so that's the maximum. And now we really have to do this optimization exercise for all grid points. So we need a double loop, 1 over capital stock and 1 over technology level. And for each pair of this double loop, we compute, we solve the optimization problem. So we optimize the maximum over a certain interval of consumption values. The smallest consumption, I put that to 0.05. That's just arbitrary, yeah. But I tried around a bit and this seems a reasonable lower bound for consumption. And the largest amount which is possible here is to consume almost everything, apart from just a small thing to avoid having too small a capital stock in the next period. So this is the interval over which to maximize consumption. Then we need the other arguments, the grid point for the capital stock. And here we choose the ith grid point of the capital grid and the jth grid point of the technology grid. And since I and j are the variables of the double loop, we run over all pairs of capital stock and technology. We also input the current value function object and the parameters. And of course, we want to maximize and not minimize the objective function. Then the optimization command will return an object, which is stored here. And there are mainly 2 parts in this object. One is the objective, that's the value that's being obtained, and the other one is the point or the consumption level where the maximal value is obtained. Here we need the value itself. So we need the objective of the maximum, and we store that for the pair ij in this new matrix. Right? We do this for all pairs. That's up to here. So that's the main part. This is actually the Bellman equation. this is solving the Bellman equation for one iteration. And then we compare the new matrix, that's the one we just computed. We compare that to the old matrix, which is part of this value function object. This is very R specific here. We look at the difference between these two matrices. This is done pointwise. Since we don't really care whether one is larger or smaller, we only care about the difference between the two, the distance between the two. We take the absolute value of the differences, and then we only look at the largest absolute value of the distances. This means the new value function iteration is very close to the old value function iteration if the maximal distance is smaller than some value. This is arbitrary. Okay, so I stop if this maximal distance is smaller than 0.001, and if it's not smaller than that, then the new iteration returns a different value function from the current one. So we put the new one in place of the old one and redo the whole thing, right? So there's a repeat command around this double loop, which runs until convergence. Okay. Any questions? Maybe we should just run that because it's really slow. And again, this is not efficient programming, but I hope that you can see the close relation between the program and the theoretical concept, the Bellman equation. So this is really well, a numerical representation of the Bellman equation and the value function iteration. Okay, so once this whole thing stops, we can actually plot the result. I stop that here and just load the object. Oh, where's that? I hope that's the right one. So I let this run for a while. I don't remember how long it takes. And then finally it really stops and you get the final estimate of the value function. And then we can plot the value function, which is a three-dimensional object, but we can just look at different slices of the value function for certain technology levels. So remember, the value function is based on two grids. One is the technology level and the other one the capital stock. And if we fix the technology level, then it becomes a two-dimensional or one-dimensional value function with one argument. Okay? So if we interpolate the value function for all the grid points of the technology level, then we get a cut through the value function for a technology level of 0.9 and different capital stocks. So we do that here. And we do that for two other technology levels, say the average one of 1 and a high technology level. We plot that. Need a bit space here. So this would be the value function for a low technology level. Here's the capital grid, capital stock running from point something to 1, and the value is negative. You remember this was the case for the deterministic solution as well, and it's the same order of magnitude. And we add the value of the value function for the higher technology level, and if technology level is higher, well, the value is higher and even higher. So these are the three cuts through the value function. And then we just add the numeric, analytical solutions. These are the red lines, and you can see that the numerical solution actually gives the right answers. We know actually in this particular example the right answer because it's solvable analytically. Normally we don't, but here we do. Okay. And then, of course, the next question is, what's the optimal consumption policy? And again, the optimal consumption policy also depends now on both state variables. So we can decide the optimal consumption as a function of capital stock and technology level. Okay, so if we want to find the optimal consumption policy, we need a matrix. And later on, we have to interpolate again. So again, we need this double loop over capital and technology. We solve exactly the same optimization problem for each pair of capital stock and technology. But now we extract not the value which we attain at the optimum, but the point where we attain the optimal value. So that's the point of the control variable which maximizes the maximum. So this is the optimal consumption in short. And we store that for this particular pair of capital stock and technology level. We do this for all pairs. This runs relatively fast, even though these are again 15,000 optimization problems. And for each of these 15,000 runs, we have to compute the expectation. Now, for each of these 15,000 runs, we have to find the optimal consumption value, which is an iterative procedure. Remember the golden section search algorithm. And for each of the values which are used for the optimization, we have to solve the expectation. Okay, we have to compute the expectation. So it's again quite a lot of effort, but compared to the value function iteration, it's almost nothing, because after one run, we already have the result. Okay, then we store that together with the grid points of capital stock and technology level in an object, which is useful for the bilinear interpolation. And if we want to simulate a path over, say, 50 periods, then we can do that. We have a capital stock, we have a consumption path. We start with a certain value of the capital stock, say 0.1, and then we have a loop over time, which runs as follows. So first, we draw the random value of next period's technology level. No. So this is done here. So we draw the technology level. We compute the optimal consumption in period T by looking at the optimal consumption policy function, which is the object that we just computed. We use linear interpolation for the current level of capital stock and the current level of technology. And that's already the result for the optimal consumption, because this object here tells us how to react for certain state of the world. So it tells us what the optimal consumption level is. And then next period's capital level is derived by, well, using the production function minus the optimal consumption. And then we have next period's capital. We draw next period's technology, and we run that over all periods. So let's do that and plot the result. And it looks like this. And if we redo that, it's different. Okay. So even though we start at the same level of capital, point 0.1, the path of consumption is different each time, because the path of consumption depends on the random draws of the technology level. And therefore, well, the optimal path is, it's a stochastic process. And this is nicely illustrated here by recomputing the optimal consumption path depending on specific draws of the technology level. Right? Any questions?
Yes, maybe one, just compared to the other examples we had, this looked like a fairly long one. So we had, if I got this correct, like 3 main steps. The first 2 being similar to what we had before. First we learn the value function, then we learn the optimal path. And then because we have the stochastic component, we have a third quote unquote thing where we simulate something.
That's right.
That's correct. Okay.
Yeah, that's absolutely right. And the most difficult part is the first one, where you find the value function, because once you have the value function, everything is easy. I mean, the value function is the essence of the optimization, of the dynamic optimization problem. If you have the value function, then you automatically more or less have the optimal policy function, which tells you what to do. And then if you have the optimal policy, then you know how the process will evolve over time. So the first part is by far the most computer intensive and most difficult one, I think. Well, definitely it's the most computational intensive one and time consuming one.
Okay, thank you. And the other thing was, you said in the theory part that with each iteration, the whole situation changes. I can't quite remember what you said exactly, but maybe you remember what that was. Like, I think the values, our grid or something. I didn't quite see that in the code where something changes each iteration.
I don't remember. So are you referring to the value function iteration, or are you referring to the simulation over time?
If it was the simulation, then that could explain that, yes. I thought it was the first part, but maybe that doesn't make sense.
Well, it does make sense in a way, because for each round of the iterations, you get a new value function, or a new current representation of the value function. You start with an initial guess, say 0. Then you compute the first iteration for the value function. Then you get a new value function, which you then use on the right-hand side, which is used to compute the second iteration of the value function, which is then used on the right-hand side for the third iteration of the value function, and so on, until convergence. So in that sense, this matrix that represents the 2-dimensional value function changes over the iterations. Maybe it was that.
Probably, yes. Thank you very much.
So what we could do as a little extension now is, I think the program is already on the LearnWeb. So what we could do is a little extension, namely to do the exercise with time dependence and the technology level. So in this example, the technology level is just an IID draw from the log normal distribution, which is certainly unrealistic. And to make it more, well, realistic, we might say that the technology level won't jump erratically from period to period, but it will evolve relatively slowly. So if it's high today, then it's relatively likely to be high again tomorrow. So the law of motion for the technology level could be written, or in this macroeconomic literature, it's often written as an AR1 process. So we have an autocorrelation of the technology level. Oh, there's a T missing here, so this should be theta T. We have an autoregressive process with a relatively high rho, say 0.9. And then if the technology level is relatively high today, then 90% of this high level will be retained on average tomorrow. Okay, so you could ask yourself how to modify the program to implement this time dependence in the technology level.